This is lecture 4.5c. By the end of this video, you should be able to explain what a differential is, and you should be able to use them to calculate and to talk about change. So what is a differential? Well, if you remember yesterday, we talked about Newton, and we did something called Newton's method, but we also mentioned at the beginning of the video that Newton and Leibniz were these two guys who, in the 17th century, both invented calculus, and then they had a big fight about who was going to get credit for it. And they essentially came up with a lot of the same ideas, but in one specific way, they kind of came at it from a different angle. For the most part, we've been in this course thinking about a derivative the way that Newton did. Newton said, okay, a derivative is the name we're going to give to the slope of a tangent line. And the way we can find the slope of a tangent line is by looking at slopes of secant lines as 2 points get infinitely close together. And this should be a pretty familiar picture. Well, Leibniz thought about them differently. Leibniz said, okay, I want to find the slope of a tangent line. And what the slope of a tangent line is really a right triangle relationship between how x is changing and how y is changing. And you can see why both of these things end up giving us a slope. But the difference with Leibniz's method is that Leibniz really was focusing on the fact that a slope has two components, a change in x and a change in y. Whereas Newton didn't really think about the two things separately. He just thought about the slope altogether. Well, differentials are related to the way that Leibniz thought about derivatives. A differential is a variable that represents a small change. The two differentials that we'll talk about most often are dy and dx. And it might be confusing, there's two letters here, but we consider it one variable. So it's like one symbol for one thing, in this case the change in x or the change in y. We could say dA or dv, any other variable we want, if we had another function. Okay, so why do we need different variables? Why aren't normal x and normal y good enough? It has to do with this picture. Look at this black triangle. Well, it's a black triangle with a pink hypotenuse. The slope of the pink line, which is a tangent line, is the height over the horizontal distance, rise over run, if you will. Well, the slope of the pink line, as far as we know in calculus, is f prime. It's the derivative of this function. So the derivative number, whatever it is, has to be the same thing as this distance over this distance. And Leibniz's idea was, well, this distance, which is a change in y, it's a vertical distance, if this triangle really were infinitely small, right down here, this distance would be almost the same thing as this light blue distance, which is how high the function really is, how much it's changed. So if this triangle got infinitely close down here, then dy would be the same as delta y, the actual rise in the function, would be the same as the rise in the linearization. And so looking at how dy is related to dx, when we're super close, is kind of the same thing as looking at how this function's direction is changing. In other words, the slope of this function. What's different about his method is we can think about the change in y and the change in x separately. In fact, we can come up with a function, and this function is the primary thing you're learning in this video. This equation right here was just derived from multiplying both sides of this equation by dx, because remember, we're now thinking about dy and dx separately. dy is a variable that depends on two things. On x, if I plug in x right here, and on dx, which is a separate thing. In other words, in order to know how much my line is going to go up, I have to know how far over I'm moving, and I also have to know where on the function I'm starting. dx, in this case, is an independent variable, something we would have to plug in, and it represents this small change along the x-axis. Okay, how do we use these things? Let's look at some simple examples. To start with a purely mathematical example, I could give you a function and ask you to find the differential. Usually I would ask for the differential dy. In this case, after we find the differential dy, we're going to evaluate it, which means we're going to get a numerical answer. And we're going to use x and dx to find it. Remember, dy depends on two numbers, not just one. Here's what the work would look like. To start, let's think about what we're trying to find. We're trying to find dy. And remember, it's really important, dy is different than just the derivative of y. It's the differential. As of right now, there's really only one thing you know about the differential. What does it equal? Exactly. dy equals the derivative function times dx, which is a different variable. So to find dy, I'm going to have to take the derivative of the function I'm given and just plug it into this spot right here. What is the derivative of the function in a? Yep, 5x to the fourth plus 37, just an easy derivative there. So I'm going to take this derivative and I'm going to put the derivative function into this spot. And then I don't do anything with dx because dx is a separate variable. It's different than x, so I can't really distribute it. And this is actually the differential. This is the first part of the problem, just like that. In the second part of the problem, they say evaluate it, which means they want me to put x and dx in to get a numerical answer. The calculation would look like that, and the decimal answer is 0.042. What does that mean? What is the 0.042 saying? Think back for a second on the image that Leibniz was thinking about. He was talking about measuring the change in y. So when we get an answer for a differential that says 0.042, this number represents this amount. And that number is related to the x value and the dx because the x value tells you where we're starting and the dx how you're changing the x value. Can you try putting that together in a sentence? If the question was, what's the meaning of this differential? How could you explain it? You might say something like, if we start at 1 and increase x by 0.001, then y will increase by 0.042. This number is telling me how the y value will change. Okay, why don't you try B and C, and again, you want to repeat the process that I just followed to find the differential. The work looks like this. So hopefully B was pretty easy, and you can just check my work. Remind me again, what does the answer mean? What does dy equals 0.06 mean? Yeah, exactly. It means that if we start on this function at pi and we go backwards along the x direction 0.02, then the y value is going to increase approximately 0.06. The approximately is important, and we'll come to that in just a second in the next example. Now, C may have tripped you up because you need to take an implicit derivative. If you don't remember implicit differentiation, take a moment to review it. I just did the work here. You should recognize all the steps. And once we have the implicit derivative, we're actually going to treat this a little bit differently. In the last example, after we have the derivative, we would have plugged this expression into the formula for the differential. But this is kind of weird because in this expression we have a y value, so it's not going to work out so that my dy only depends on x and dx. I would need to know a y as well. And that's no good. But there's an easier way to get to your differential. Remember, y prime stands for the slope of the tangent line. This is the derivative. And the slope of a tangent line can also be written as dy dx, because that's just Leibniz notation for derivative. So if I'm trying to get dy by itself, what could I do to both sides of this equation? Right, I could just multiply dx on both sides, effectively canceling out dx over here and moving it to that side. And that would give me my differential expression, just like that. And the only last thing I need to do is I need to figure out what y is. There's a couple ways you could do this. Since we know that x equals 2 and we're really interested in one particular value, I could plug in 2 to this expression and solve for y. Or I could solve for y as a variable and plug it back in. For the purposes of this video, I'm going to leave your answer in this format, and we're not going to check the numbers, but you should see more or less how it could work, and it wouldn't be too terribly hard. So now that you've seen some math examples of where we talk about differentials, really why we care is because they're very useful to talk about change in the real world. We use differentials to estimate how something is changing. For example, let's say we have a circle, and we want to increase the radius of the circle from 10 meters to 10.1 meters. We would use the differential for area, dA, to estimate how the increase in the radius affects the area's increase. In other words, we have information about how the radius is changing, and we're looking for information about how the area is changing. I'll explain what this last sentence means after we start this first half of the problem. As with any word problem, the ticket to success here is going to be being really clear on what you're trying to find and understanding what's been given. Read this over again to yourself. What specifically are we trying to find? That's right, we're trying to find the increase in area. And I want to just observe, increase is a word for change, which tips us off that this is a differential. dA represents the change in area. What are we given? Right, we're given that the initial radius is 10 meters, and then I could write that it changes to 10.1, but there's a better way to represent that. If the radius is changing, what variable would I use to represent the change in the radius? Right, you might be picking up on the pattern here. dr is the change in the radius. And in this case, dr is 0.1, because to go from 10 meters to 10.1, the radius had to change by 1. So I know an r value and a dr value, and I'm looking for a dA. We're going to need some sort of function that connects the two. And in order to write the function, you need to know what the output should be and what the input should be. Looking at this situation, what do you think the input is? What do you think the dependent variable is versus independent variable? That's exactly right. The dependent variable or output is going to be area, and the input or independent variable is going to be radius. I was clued into that because we know the radius and the dr. And if you remember, when we're doing differentials, this differential depends on both x and dx, so I'm kind of thinking that radius is going to be the input. It also helps that I know the equation for the area of a circle, which is pi r squared, and that's just an easy formula, or in this case we're thinking of it as a function, to start with. So we now are set up with everything we need. We just need a way to get to the actual answer. Well, I know I'm looking for a differential here, and it's the differential of an output. What does this differential have to equal? Exactly, it has to equal the derivative function times the differential of r. So all I need to do is figure out the derivative. That's pretty easy. That's just a normal power rule. Remember, pi is just a number, so there's no product rule. And then I just plug the differential equation in to the two pieces. And finally, I can plug in the radius and the dr value. And we end up with dA equals 2 pi. But you're not done unless you can explain it. Remind me again, what does that mean? I would probably put it as an if-then statement. If we increase the circle's radius by 0.1 meters, then the area will increase by 2 pi meters. That's kind of surprising if you think about it. It's not wrong, it's right. But a tiny little change in the radius actually makes a pretty big change in the area. And so this is actually where we're headed next, talking about change.